Hello everyone, my name's Morgan. I'm a mentor for MDFS1. Today I'll be quickly walking through the Mechatronics Demonstration. Okay, so let's get started. Okay, so our Mechatronics Demonstration controls three different motors: a stepper motor, a servo motor, and a DC motor. Okay, so to turn it on, first of all we have our battery here. It's connected to a fuse and a switch, so we switch the power on with this switch, and then we have another switch which is a digital enable switch. So we'll do that, and then everything's off right now. No motors are working, no feedback. Digital enable switch will turn it on to our first state. So in our first state we're controlling the stepper motor. To start off with, we're controlling the position of the stepper motor. Then we have a button over here. This button will switch between controlling the position and speed, just for the stepper motor, none of the other motors, just the stepper motor. So we can see that now. So now we're controlling the speed, goes forwards and backwards, and we can switch back. Right. There we go, see? Now we can move on to the second state, which will be controlling our servo motor. So we can use the switch motor button. Now we're controlling the servo motor. We're controlling the position only. The servo will only turn between 0 and 180 degrees. Right. Now we can move on to our next state by pressing the switch motor, and this will control the DC motor now. So we're controlling the position, the speed, forwards and backwards of the DC motor. We aren't controlling the position, though this is possible because this DC motor comes with an encoder on the back. This isn't hooked up right now, but that is an option if people are looking to control the position of a DC motor. Right, in our last state, we're going to control all three motors at once. Right. We control the position of both the servo and the stepper at the same time, and also the speed using the linear potentiometer here. And that's it. So our circuit starts with a 15.2 volt battery into an XT60 connector. Our red wire represents our voltage high, and our black wire represents our ground. It's important to keep this consistent throughout the rest of our circuit. Straight out of the XT60 connector, we go into a fuse, a 5 amp fuse, and this has been tested for this circuit and it's perfectly fine. From our fuse we go into a power enable switch. This is not a digital enable switch, it's just to turn the power on. It's not a single start switch, just to enable power. This goes into our Wago connectors, which connect up the rest of our circuit to our voltage high and ground. It's important to use Wago connectors or terminal blocks where possible. They're much more reliable than, say, DuPont connectors, and even more reliable than soldering. Even if you do solder, you need to make sure you use heat shrinks over all your connections. And for your Wago connectors and terminal blocks, you need to make sure you don't have any exposed wire. From our Wago connectors, we go into our buck converters. Our buck converters step down the voltage to use in the rest of our circuit. You set the voltage outputted by the buck converters by adjusting the onboard potentiometer. Then, whilst you're adjusting the onboard potentiometer, you measure the output over the negative and positives. You set this depending on what other your parts in your circuit require. We have fuses placed after our buck converters, so we go through our buck converters into our fuses and then power our circuit. This is to prevent overloading our buck converters. These fuses are 2 amp fuses because our buck converters are rated to 2.5. It's important that we secure all of our components using nuts and bolts. Don't use hot glue or other glues. This goes for wires as well because our electronic components heat up and then the glues come loose. Alright, so only use nuts and bolts. It's also important to label our components to prevent confusion when wiring things up. Okay, this is our L298N motor driver. It can be used to drive both a stepper and a DC motor. However, in this circuit, it's only set up to drive the DC motor. These have a variable voltage drop depending on how much current you're pulling through them. So what this means is that between our buck converters and our driver and our motor, it can have a variable voltage drop of anywhere between 1 volts and 5 volts. This is an important consideration. for your design. They also don't limit current, so it's important to consider that as well. So our servo motor actually has a motor driver built in. So what this means is we just need to connect it using a signal PWM wire and our power and ground. This makes them very easy to use because we don't require an L29N driver or any of our other drivers. However, an important consideration when using our servos is that they pull a lot of current. So you need to refer to your data sheet to determine how much current that's going to pull. Alright, so let's take a look at our A4988 stepper motor driver. These drivers can be used to control only stepper motors, such as this one here. One of the benefits of our A4988 is it has a current limiter built in. However, this current limiter can only safely pull about 1 amps without frying the driver. To set the current limiter, you need to adjust the onboard potentiometer to have a voltage reading of 0.7 to 1. That's this potentiometer here. This is referred to as VREF. If you go look online for some tutorials on how to set up the current limiter, use VREF as a keyword. Our stepper motors move in discrete steps. Alright, this is how we control our stepper motor. To set the size of your step, or the size each step turns, you can adjust the 3 MS pins down one side of the driver here. For our A4988s, we also need to use a polarized capacitor, which is this shown here. If you do not use a polarized capacitor, you will fry your driver. Our polarized capacitors have a positive and a negative. The negative side is denoted by the white band shown here. If you connect your polarized capacitor incorrectly, you will blow up the capacitor. So make sure to get your mentors to check it over before turning it on. It is good practice to avoid using breadboards such as this one for anything other than prototyping. Instead, use a shield or something similar, as all the wiring and everything's already done already. So if you're using a stepper motor in your robot, consider using a shield such as this one. This shield goes on the top of your Arduino Uno. It also fits on top of Arduino Megas. And you can also see that it has the polarized capacitors already built in. So all you have to do is put the driver on the top. This is very important because if a wire comes loose on our breadboard, we will destroy our driver. This is just because they are very fragile. Just some other important things to mention. Make sure to get your mentors to look over your circuits before powering them on. Also, always use power supplies to test your circuits initially. Batteries are one of the last steps in the process. The power supply allows us to test our circuit safely. And only once our circuit works as expected and we know it's safe, can we then hook up a battery. And lastly, I encourage you to go look online for data sheets and other tutorials to learn more about setting up your drivers and controlling your motors. And that's it.